Okay, good morning. So as you probably know, Phil is on travel, so I'm here in his place. The topic here is about dense linear algebra for today's lecture. And I work at Lawrence Berkeley Lab up the hill. My name here, my email, in case after the lecture you have questions or something. And I was a student here a long time ago. I got my PhD with Jim Demo. So he was my advisor. So the topic is really dear in my heart. Okay. It's not moving the slides. Oh, what happened? Okay. Okay. So this is the outline of the lecture, and I think a lot of people know about dense linear algebra, and we can go that quickly. And the main thing is to talk about how to get high performance, how to structure the software, writing the good code, so that when these kind of algorithms run on current machines, you can get a very good speed out of the machine. And in particular, this lecture, we're going to just talk about in very much more detail the two algorithms. One is the basic matrix multiplication, and another one is the basic algorithm Gaussian elimination to solve linear equations. So what is dense linear algebra? There are a lot of functions in dense linear algebra. It's not just the basic linear algebra subroutines like BLAS, people if we are familiar with. So you have routines to solve linear systems, to solve least square problems when the matrices are rectangular, and to solve eigenvalue problems. It could be standard eigenvalue problem, AX equals to lambda x, or generalized with the two matrix pairs, and also singular value problems, etc. So then there are different levels of details in terms of coding these algorithms, and also from the user point of view. So you can have a simple driver, just a simple linear system, but you can have expert drivers which can deliver the error bounds to bound what's your solution accuracy, and also to deliver the condition number, compute the condition number, which is the estimate. And sometimes if the matrices are very ill-conditioned, you need extra precision. And also from the matrix structures, there are a lot of different types of matrices. So there could be real complex, of course, and then there could be symmetric, Hermitian, positive definite, or general non-symmetric. So I'd like to ask how many of you at least have seen any of this topic or have used any of these dense linear algebra routine in your research, in your class? If you may raise your hand. So that's a fair amount. Yeah, that's pretty good. So then you're, we can, skip some of the basic algorithm side. So let's take a look at matrix multiplication. And if you suppose you are familiar with matrix multiplication, then you can know that usually you can just write a nested loop, A matrix times a B matrix, write a 3 nested loop for I equals to column, and for J equals to each row, and then for K equals to 1 to N. So the simple nested 3 nested loop. But the performance of that simple algorithm, it's 3 lines, several lines. And you will get the performance is like this. So in this chart, I'm plotting the horizontal dimension is the matrix dimension, and we're talking about a square matrix in this case. So the vertical dimension is the gigaflop rate, which is the measure of how fast your floating point operations can go. So you can see that with the naive 3 nested loops, you get the performance is miserable. The peak performance of this machine is over 300 gigaflop. So this is the megaflops. But with this straightforward algorithm, you get maybe 10% or even sometimes less than 10%. And then in this picture, there are 2 more curves. One is the blue one is the red one. So the blue one is, let me see, is a package called a fee pack, which does some auto-tuning, which we'll cover in this lecture, to get instead of a simple three nested loop, but it's blocking a lot of techniques. And the red one is the vendor provided by Sun performance library. So the vendor, the hardware people, they know how the hardware architecture looks like. They can do a lot of hand tuning. And you can see that with this auto-tuned library, the speed can be almost as good as the vendor, the people who are doing the hand tune code. So now the bigger question is, where does the time go? Why your three nested loops cannot get a very good performance? In the old days, when we do algorithm analysis, we only talk about floating point operations. For example, if your algorithm has order of n square operation, which is certainly better than n cube, for the algorithm scaling is better. But that's just a very small part of the story in nowadays machine, because the memory access is much more expensive. So this picture essentially shows you the speed when you do the computing on the real machine. What are the speed? What's the time spent? So at the closest level to the processor, you will see these blocks. You have floating point operations happening here, and then you have maybe 30, 60 registers here. They can be very fast. And the on-chip cache is also relatively fast. So if everything computing is at this box is at the fastest possible, so that's you can get the peak. But on the other hand, the cache memory is usually small. So you need a bigger memory, which has to be built at a lower latency, at bigger. And from a static RAM here or from dynamic RAM, it's even bigger, and the secondary disk, etc. So essentially, the time listed in the bottom table there is the speed. So the speed is getting lower and lower when you increase the size. So the size is getting bigger, but the speed is lower. So the art of programming, getting high speed, is really to get a lot of data at the fast memory, and not to access data as often on the slow memory. So try to reduce the access to the slow memory, which we usually call the common generic term for this is communication. So you can see that the speed difference between the processor growth and the memory speed growth is also at a different pace. So the processor growth, normally it follows Moore's law. Every year you get about a 60% increase in the CPU speed. That's good news. But on the other hand, the bottom curve is the dynamic RAM, DRAM. The performance grows only at 7% of the per year over the in the historical data here. So you can see the gap is getting bigger, which is really a bad news. So if you just focus on the floating point operations, you don't do anything in terms of avoid memory access, avoid communication, then the algorithm will be relatively slow on newer machines. And obviously, in order to analyze these algorithms on the new machine, on today's machine, we need a good performance model, so that you capture both the floating point operation side, also capture the memory communication side. So here we usually have several parameters to look at the machine architecture and the algorithm, the combination. So M here is the number of memory words. For example, the elements you moved between fast and slow memory from DRAM, for example, from DRAM to on-chip cache. So that's the number of the communication volume, you can say. And T sub M is the time per slow memory operation. So how long does it take to access one data item from DRAM? And then F is the number of arithmetic operations, floating point operations. And T sub F is the time per floating point operations. And one of the important things in this equation, in this model, is this ratio of M over F over M, the Q. This quantity is very important. Is the average number of flops per slow memory access. And we will see that this actually is critical most critical component to determine the actual speed on the real machine. So in the old days, when we don't worry about memory access, the time is just the flop rate, the number of flops times each flop the time. So that's the old formula. And it's not good at all nowadays. So the actual time is actually the floating point operation time plus memory access time. So you have so many data you need to access times each the time per data. And here I'm assuming that there's no overlap between the floating point operation and the memory access, so they go. But even if there's an overlap, you get at most a factor of 2 better. Okay, so it's if you consider overlap, it's going to be the max of the 2. But let's say forget about overlap. So just these 2 time, they need to be added together. And when you factor out the floating point operation time, this term, then you add this, factor out this factor, then you have 1 plus this quantity. So that's the machine balance, this machine time for memory access and the time to do the floating point operations. So you can see that if this ratio is smaller, the better. You are going to get, then it's divided by Q, so you get into the whole quantity will be smaller. So a good machine will have Tm divided by Tf, which is a factor of as small as possible. But in practice, this is usually several hundred times the difference. The ratio can be huge. So as we saw from the previous slide, when you access DRAM, the time could be several hundred nanoseconds, but the floating point operation is just 1 nanosecond. So the ratio of this guy is actually very big. So you need a Q. Therefore, your arithmetic, this computational intensity, which is number of floating point operations per memory access, needs to be big in order to counteract this big machine ratio. Any question? This is the probably most critical part of the performance model for the lecture when you do analysis. Yes?
Does this simple formula assume that you only have one arithmetic register?
Actually, you can have many registers, and then you can have multiple cache. It's I would say this simple model. It doesn't talk too much about how fast it's in the register. It's mainly talking about on the processor side, it's one speed. On the DRAM, it's another speed.
Okay, but if you have a bottleneck of the memory access, but you can do many parallel arithmetic operations
right.
to equal the bottleneck on the other side, I assume you're going to get towards that direction eventually.
Right. Yeah. Okay. Yeah. So which is say vector operation, let's say. Then it's even each TF is even smaller, right? And you need to make sure that you feed the data into the vector register. You need to feed very fast, otherwise the processors will be stalled. Okay, so keep in mind that you need the arithmetic intensity like maybe at least 2 orders, maybe 3 orders magnitude in order to get a good performance. And even with this break-even case, you have a ratio of 1, so you get only half of this peak. In order to get 90% of the peak, you have to do a lot more. So that's something we'll do step by step. So let's start with a simple operation, matrix vector multiplication. Here you have a matrix A, and then you multiply with X plus this destination vector, then put in this destination. So you need to read this vector. So you need to read this X vector into the fast memory. We are thinking about a cache. And then read Y vector. Also, you need to read a row of matrix A into the fast memory. And then you do this most inner loop here is just a dot product. The 2 vectors do the dot product. So it's one row of the matrix dot product with the source vector X. this gets to one entry of y. But of course, you need to get all the entries of y, going through all the rows. So let's look at the counting of these different parameters. So m is the number of slow memory reference. Here we have to do 3 read of the vector, 2 read vectors and 1 write vector. So that gives you 3n. And also we need to read the matrix A, which is n squared. So it's 3n plus n squared. And f is the number of operations. So here you can do the count. We usually count operation plus and multiply is separate. So each plus is 1 operation, each multiply is 1 operation. So here it's 2n squared because it's separate plus and multiplication. Then you can compute the Q. This ratio is pretty bad. It's only 2. Okay? So with this algorithm, you won't be able to get a very good performance on the machine. So then we move to the matrix multiplication. Here you have a lot more operations. Let's see whether we can do better. So the matrix multiplication, as I mentioned, it's 3 nested loops like this. So outside you get so C matrix you need to get n squared elements. Okay, and what does this algorithm do is basically loop goes through 1 row at a time. In the inner loop here, we get Cij, which is this guy, corresponding to 1 row of matrix A times 1 column of matrix B. So that gives you only 1 entry. And then for the entire row, you will need to take 1 row of A, multiply every column of B to get the entire row of C. Of course, to get the entire matrix C for all the row loops outside here for I from 1 to n rows, then you will need to go to the first row of A, multiply with the entire matrix B, go to the second row of A, multiply the entire matrix of B. Okay. So in this case, arithmetic you can count is order of n cubed. And then it operates on how many memory words? It's 3 matrices. So it's roughly 3n squared. So then you can have a Q ratio, which is potentially could be very good, could be order of n. So that means when you increase the matrix size, potentially you can get a very good performance. But then if you look at the naive algorithm, it actually does a lot more memory access than necessary. So here is we count the number of memory access here. Read row I of A into fast memory here, and then read Cij into fast memory. The inner loop is read column J. So in fact, matrix B has to be read like n times. So inner loop is read n columns. It's 1 matrix B, and then when you sweep all the rows, this B has to be read many times again. So then the count is here. So n squared total reads for row I of A, and then n squared total reads for Cij. Okay. Then n cubed total reads. Remember, this is n cubed over the reads for B. That's really the killer here. So and then the write is n squared. So the killer is it's reading B many times, n cubed, even though B has only n squared entrance, right? And of course, suppose your cache memory is large enough to hold B, hold all 3 matrices, then it reads only once. But that's not usually the case. So let's do the calculation now about this model. So look at the M, which is the number of words we read, just this naive algorithm, is n cubed, which is to read B n times. And then n squared to read each row of A each 1 time, 2n squared for C matrix. So in the end, the bottleneck is B n cubed. And then you compute the Q ratio. It doesn't help. It's not improving. It's 2. And the problem here, the failure of this algorithm is not the computation, this matrix multiplication algorithm itself. It's just the way you organize the algorithm. You read it too many times for B. So that's something we need to fix. Because remember, potentially, this Q ratio could be order of n. Okay. Okay, so let's see here. What we do, the first technique in this lecture, the important technique is the blocking. So what you do is instead of doing one element at a time, here each of my block here is just a block of size b by b, let's say. Okay, that's different from before. And the loop is the same, but the difference is at the inner loop. So the number of loop bounds will be n over b, because here every time you have a b, the granularity is a b there. So the inner loop is a block of 3 matrix blocks of size b by b, okay? And otherwise, the algorithm is the same. It's not changing. But just with this little twist, then you can see that the counting here becomes much better already. And here we are doing the operation slightly different in different order, but then the so that means that the amount of number of floating point operations is the same, which is 2n cube, okay? But then now we compute this q factor. So q factor is now with each block of b, n over b cubed times. Still there's a cubic, n over b cubed times, okay? But then each block is b squared. So the total data item you read is actually n over b cubed multiply b squared. So which is n squared over b. It's better now, n cubed over b, which is better than n cubed, right? So fewer than n cubed. So that's what's happening for B matrix, for A matrix, similar for C matrix. And in the end, you got a factor of B better. So the Q ratio computed using this algorithm, you get a factor of B better. Before was 2, remember? So then the question is, of course, you want Q ratio to be bigger is better. You want to be as large as possible. The question is, how large can you go B? You cannot do too large. Since you are limited by the fast memory size, you want these 3 matrix blocks to be able to be on the fast memory, the L1 cache, on-chip cache. So the cache size limits your B size. That's this calculation here. So what's the limitation of this algorithm in order to do the optimization? So the number for slow memory references we did the calculation is here. You can increase B, okay, but the problem is suppose the fastest memory cache, the size is M, then your 3B squared has to be smaller than M, okay? You cannot have B bigger. So that's the limitation. B cannot be too big. You want B to be big, but it cannot be too big. So the tiled matrix multiplication cannot reduce M below this quantity, because if you just do the calculation, B has to be smaller than this, and then plug in this B into this Q ratio. Plug this, the limit of B into this Q ratio, then you will get the memory access M cannot be smaller than that, has to be bigger than this. So there's a square root of M, the cache memory size at the bottom here, okay? Any question? Okay, so in very early days, in fact, this lower bound was already shown in the historical paper here, that you cannot do better than this. So this discovery was not recent, it was a long time ago in the theoretical analysis. So essentially it says any reorganization of this algorithm. We were just here, we were talking about one type of blocking algorithm, but this paper is more general. It says any reorganization of this algorithm is limited to the number of slow memory references by this n cube divided by square root of M. Okay, for any, no matter what you want to do. Okay, so that's the lower bound. And more recently, Jim Demo and his co-authors, they proved even further, more generalized than matrix multiplication. So in this theorem, they say that consider any algorithm. In dense linear algebra, a lot of algorithm, it looks like 3 nested loops. Looks like matrix multiplication, but it may not be matrix multiplication. and running with faster memory size M, then no matter how you optimize it, essentially no matter how you reorganize the algorithm, if you just use associativity and the commutativity, then your number of slow memory references is bounded by the number of flops divided by the square root of n. Okay, so that's a more generalized to the previous theory. So this includes a lot of the dense linear algebras. And in fact, in a lot of dense linear algebras, the floating point operations is mostly n-cube operation. Okay. And for sparse, it's much better. But the analysis for sparse matrices, for general sparse matrices, is very limited. It's difficult to do. So there's still a lot of work to do. So right now we're talking about a sequential, just moving data between memory, slow memory to faster memory. This more or less carry over to the parallel computers, that where you move data from different computer to another computer to do the communication. So it's essentially the same idea. And a lot of the analysis, a lot of the practical aspects are covered in the course CS267. How many of you heard about this course? Oh, you take some of you taking this, talk this before? In the spring, yeah. So that's a very nice course about doing parallel computing. And also avoiding communication is even more important, because there the speed of communication across the network is much slower than DRAM access. Okay. So now the question is, you know the lower bound. How many algorithms right now, for example, currently, they attain these lower bounds? And there are not a lot of them they attain. Some of them they do. So in the good design, you can attain these lower bounds. So then that's why we encourage people, if you need to use linear algebra in your work, in your research, in your anything classwork, try to use this very good public domain software as much as possible. So for example, for the sequential code, LAPACK was developed when I was a student here. So I was very much involved in the LAPACK, ScalarPACK development. So even after 20 years or so, these packages, they are still the gold standard for people to use them. And there are still new algorithms coming out of those packages. And most of the vendors, they actually provide versions of LAPACK, ScalarPACK. They can probably tune some of the kernels on their machine based on their hardware, and they can get the algorithm the higher level algorithm, like a linear solver, eigensolver, go much faster. But for some problems, some problems like a matrix multiplication, the lower bound, they cannot be achieved yet. So even though sometimes the algorithms in these libraries, they don't achieve lower bound, but in practice they are still very fast. So let's go deeper to two examples to look at the further optimization of matrix multiplication and the Gaussian elimination. So now the question is, we talked about matrix multiplication doing the blocking with a two memory hierarchy. One is the fast memory on-chip cache, one is the DRAM. And we do this blocking. We still do 3 nested loops, but with a block size there. That's tell the algorithm. But the thing is, on current machines, very often there are more than 2 levels of memory hierarchy. So it could be fast cache, the L1 cache on the processor, and then the L2 cache, which is off processor, and then DRAM, disk, etc. So you can imagine that in order to deal with different levels, L1, L2, DRAM, let's say 3 levels, then you need to do 9 nested loops, because you need a different block size for each set of 3 nested loops, which you want to fit into one level of the faster memory. So that's why it's exponentially exploding if you have more memory. Of course, it's not going to be portable, because different machine this machine has 2 cache, the other machine has 3, and their memory organization is different. So you can imagine that you can have write a lot of different versions of the algorithms. And that's what's the nice thing about this cache oblivious algorithm coming into the picture is an alternative way of looking at the problem instead of saying blocking at each level manually. And we're trying to see whether there's an automatic way to fit the block to do this in the top level so that you can fit the block size naturally at each level of the cache in a nested way. So that's essentially use the technique, the recursion technique. So here I give you the simplest case when the matrix dimension is power of 2. And then you can configure the matrix as 4 quadrant pieces. So you have 4 pieces, 1, 1, entry 1, 2, block 2, 1, 2, 2. So in the beginning, if your matrix is very big, each of these blocks is big. You just cut in 4 pieces. And then your block operation here is straightforward. You just add, multiply each block like this. Okay, but then this block you can still do recursively. So that means you have how many multiplications? You can 1, 2, 3, 4, 8 multiplications, and then 4 additions. You do this recursively until you get down to the 1 element or several element. So then we can count the operations in this recursive scheme. And because it's this recursive relation, you can write down A, the operation relative using the dimension n, which is 8 times A of half of the size. Okay, the same operation, but half of the size. 8 of them. Remember, we have 8 of them. And then the lower order term is 4 of those addition, which is n over 2 square. So that's the lower order term. So when you write down this geometric sequence, adding them together in the end, it's still 2n cubed. You're not saving the floating point operations. Here, you're just changing the order of operation. Okay, so that's the important point. And then now we count W, which is interesting here. So W is the number of words moved between fast, slow memory by recursive algorithm. And similarly, you have the same relation, 8 of those half of the size, W half of the size. And then lower order term is 4 of those n over 2 square, okay? And also I add this together, so it's going to be n cubed divided by square root of m plus the lower order term. So it's the same as blocked algorithm. From a performance point of view, it's not improving from this model we're using. What it's improving is you don't need to write many different codes. You don't need to do different kind of blocking, 9 nested loops to do different blocking to fit different cache. And this recursion naturally, when you get down to the bottom, it will, at intermediate point, it fit into maybe L3 cache. At next intermediate point, fit into L2, and then when you get the bottom, fit into L1. So that's the advantage of this. So performance-wise, 2 algorithms you can all write nicely to block the version or recursive version. You can all implement nicely. They can all achieve almost 90% of the machine peak. Okay. Now let's look at Gaussian elimination. So Gaussian elimination is probably one of the most popular tools to solve linear equation AX equals to B. Essentially, what it does is it needs to add multiples of each row to later rows to make A upper triangular. And also after this process, you make the lower part of A lower triangular. So in the end, you get A equals to L times U, 2 triangular matrices. Then you solve the triangular, use the triangular solve. So the loop here is organized very similar to the matrix multiplication. It's still 3 nested loops. But here, we are working with triangular matrices. So the difference is the bound, loop bound, is slightly different. So here we don't, the outside is running from 1 to n minus 1, it's the n rows. But the inside, you see the bound is not from 1 to n. Instead, it's from j plus 1 to n. So it's the rectangular part. And also the most inner loop is from I to n. It's also the corresponding to the triangular part. So at the outer loop, it's looping for each column I, and then the next loop is for each row j below row I. For example, if currently I'm at row I here, and then I look at all the rows below this ith row, okay? And the most inner one is from I to n, which I need to do the update of jk entry, which is corresponding to this part. I need to do the update. Each entry is subtracted by this scalar, multiply the aik, which is the ith entry, and then the kth entry here, okay? So here is add a multiple of row I to row j, which is this guy. So you do this after looping through n columns. In the end, you get the upper triangular matrix, and the lower one, we'll see what is the lower one here. You essentially zeroed out the lower one, but then there's a multiplier, which is recorded. So we'll take step by step of this operation. So first, the optimization is we remove this constant, put this to the outer loop. So one trick here is that in the inner loop, you have division. Division is usually much more expensive than multiplication addition. So division could be like 10, 20 times more slower than multiplication. You don't want to do division as many times as you want to reduce the number of division. So that's one trick we use is putting out this division. It's constant relative to this loop. So we just put this out. So that's the first thing. This multiplier, we call this multiplier, do this, and then inside is a constant multiply this. It's a scalar vector operation. So that's the first refinement. And the next one is what you have computed, then you don't need to recompute anymore. So you don't compute what you already know. So the loop here, instead of from I to n, you just need to from I plus 1 to n, just to do something below the current diagonal, okay? And then here, you store the multipliers m below the diagonal in zeroed entries for later use. So remember, this m is your multiplier. In the end, you need this to solve the linear system, to do the triangular solve. And you don't want to, since the storage is already there, matrix A is already there, the lower part is going to be zeroed. Then you can use this lower part to store your multipliers. So that's what's happening. This m is actually stored in the lower part. So all these AJI, for j bigger than I, it's going to be storing this multiplier, okay? So in the end, you still, starting with matrix A, then in the end, your lower triangular matrix L is just populated here. Upper triangular matrix U will be populated here. You don't need extra storage. So this is, can do this Gauss elimination in place. Okay, and then also you can split the loop. Another optimization is here you compute the multiplier, right, for each column. And then for each of the multiplier, you do this. But in fact, all these multipliers, they can be computed in a separate loop before you apply this update. So that's what this split the loop is doing. In this loop, you do compute the multiplier for the one column, and in the end, this is going to be the L matrix. And then for the rest of the submatrix from these two loops is the trailing submatrix from I plus 1, the column, and then j plus 1, the row. So the trailing matrix, you do this update. Okay, so then so that's the algorithm description. And in terms of practical implementation, what you do is you can use lower level matrix operations to support this higher level Gauss elimination, LU factorization. So this picture shows what are the operations is needed and what can you call the good library. We can call this a BLAS library, okay? So the picture here we're looking at the ith column, and everything on the left is already finished. Those are the multipliers we already finished. And everything up here above the current ith block is already finished, the U part, okay? Then we're focusing on the current step. Current step with ith column, ith row, and you need to compute the multiplier. You have the multiplier here, and then you need to use this multiplier times this A part, update into the destination to do this subtraction. And then you can write this algorithm in BLAS operation. We'll talk about BLAS soon. So the scalar, this to compute the multiplier is just a BLAS1 operation, scale a vector. It's this column divided by one entry. It's actually multiply the reciprocal of this entry. So that's BLAS1 operation. And then this one is a BLAS2 operation. It's a rank 1 update. So essentially you take the whole column here, the whole row here, and then multiply them together, update into the whole matrix. This is like an outer product, if you want. So that's called a rank 1 update, BLAS2. So then what does this GE really compute? And then what are the operations? What's the memory access? Then we can see very shortly. So this operation is BLAS1, then BLAS2, right? Then you wrapped around into n columns, call this. So we call this a strictly lower triangular part of the matrix. The multipliers is, in fact, we call the L matrix, which is just the identity matrix plus all the multipliers. So that's I plus M. And the upper triangular matrix is just the U. The algorithm we just talked about will terminate if you don't divide by 0 at any time. If the diagonal element is not divided by 0, then in the end you get A equals to L times U. After that, you can solve this equation by first do the forward solve using the L matrix, get Y, and then do the U matrix to do the solve using the Y as the right-hand sides to get X. And the operation count is the most expensive one, is this LU factorization process. Remember, we still have 3 nested loop. So it's still going to be n cubed, similar like matrix multiplication. But then the constant is smaller because we're working at within each loop, the bound is not to n. Inner loops the bound is not, upper bound is not from 1 to n. It's actually looking at shorter and shorter vectors, the row column vectors. So that's why in the end, after you do the summation, it's 2/3 of the operation. Okay, so what's the problem with this basic GE algorithm? And similarly, it's still related to the BLAS operation, how fast you can go. Because remember, in the basic algorithm, we're just calling the BLAS1 vector scaling, and also calling the BLAS, another BLAS1, which is BLAS2, which is the rank 1 update. And this picture shows what's the speed of BLAS1 and BLAS2. So here you have the order of the vector. So on the horizontal axis is the size of the vectors or matrices, the dimension n. Okay. Vertical axis is the speed in terms of megaflops. So the higher, the better. So on this particular machine, it's I believe this is an earlier benchmark. But even if you do the benchmark on the recent machine, you get pretty much similar picture. So you can see that BLAS1, BLAS2, they get a very low speed compared to BLAS3. So that's still the issue is we want to change this algorithm. Instead of using BLAS1, BLAS2, can we do BLAS3? Okay, so that's the goal. And the way to do that, here we show you you can still do the blocking. So you can still configure the algorithm as three nested loop using the each loop n1 to n over b, and the internal operation will be the BLAST2 for the scaling, and then the BLAST3 for the big trading matrix update. So that's still blocking still works. But in here, I'm showing you the cache oblivious version, which is has a better advantage. It's slightly better than the blocking version because it's automatically taking care of the different cache memory. And that was proposed almost 20 years ago now. Okay, so this we describe this algorithm in a simple case, still without pivoting, just everything on the diagonal is good. So what you do is still configure your matrix A as a 4-quadrant, okay? And then you suppose this matrix can be factored Gaussian elimination into these 2 blocks, this side and that side. And this lower part is 0, this upper part is 0. So that's L matrix, U matrix. And you multiply out all these blocks by algebraically equating this A matrix with this matrix blocks. You can see that all these 4 different equalities we need to maintain, and then you work out what's the operation we need to do. So for example, for the first block column here, A11, A21, we need to satisfy, they need to be equal to this block column, okay? So these two should be equal. So which corresponding to, you do a LU factorization for rectangular matrix, and the U is a square matrix. So this will be the same problem with half of the columns on the left, right? And then you solve A12 in order to get a U12. So here we need to get U12, which you need to solve A12 equals to this. It's a lower triangular solve to get U12, okay? So you call the triangular solve, which is BLAST3, because here we have everything is blocked, so it's BLAST3. And the third step is for A22. A22 needs to be equal to S plus this guy, okay? So that means your S has to be A22 minus L21 times U12. So this is, you can see that this is a matrix multiplication routine, and it's BLAST3. So the last step is after you get this S, which is smaller, half of the size of the original matrix dimension, then you get do the LU factorization again. So then that becomes the same problem with half of the columns, fewer rows. Okay, so that's how this recursive algorithm works for the GE. It's slightly more involved compared to the recursive algorithm for the matrix multiplication. But as long as you are able to write down the algebraic representation by equating the different blocks, then you know what are the operations are needed. But then the advantage you can see here, all the matrix operations here are BLAST3 operation. So naturally, suppose the vendor gives you a very good BLAST3 library, then you are good performance. You don't need to worry. So this one is just showing the how the algorithm is implemented in when you call this function recursively, recursive LU of, this is the left half of the A, and the bottom here is the right half of A, and the middle is to take care of the U12 block and also the big short complement update. And similarly with this, you can do the calculation to count the number of words moved to factor this m by n matrix. So this matrix could be rectangular, m by n. And the relation is the left half is given by this recursion. So the memory access will be this one corresponding to the left half. And then the right half is given by this quantity, which is the memory access needed for the right half, half of the size. And the middle one is just the memory access for the U12 block and then the trading matrix update. So by doing the arithmetic calculation here, you will see that in the end, the number of memory access is roughly of order m times n squared, still divided by the m square root of m, which is the fastest cache size. And assuming that this quantity is roughly the same as this quantity, if these two are of the same order, then you get, this is your bound, the memory access bound. And it's very similar to GEMM, the recursive algorithm. It's the same. It's the same as the theory. Shows that it shows that the lower bound to compute any three nested loop is given by the floating point operation count divided by the square root of m. So that matches the lower bound. Okay, so that's about two cases that we have covered in step by step about the optimization. And then I will spend some time to talk about some way to automatically writing some code to get a faster speed. So some of the other topics here is, so you see it's very nice to have these cache oblivious algorithms. But in fact, it's not always, it doesn't solve all the problem. First of all, when you're recursing down to problems of size 1 or 2, it's a lot of overhead in the recursion. So in practice, the recursion is actually adding a lot of overhead in the stack memory, etc. It's not always fast. So most of the implementation right now in this high-performance code, the BLAS and the ScalarPack, LAPack, etc., they are not recursive algorithms. It's just the practical side of the issue. And then usually even for these recursive kind of algorithms, you need to switch to block algorithms at certain stage. You don't want to go to very bottom of the recursion. So sometimes they do recursion maybe just to a couple of levels, okay, depending on your cache memory size. And the algorithms for the other linear algebra operations is actually much more complex. So SVD, eigenvalue calculation, etc., they are not easy to be organized as this cache oblivious recursive way. So still, blocking technique is very useful. It's most prevalent. And then another thing is, suppose you want to reduce the number of floating point operations. There are some algorithms to do that. Right now, most of the common libraries, the algorithms we implement is order of n cube operations. So there are algorithms, this order of n to the w, this w can be smaller than 3. For example, for matrix multiplication, Stranson's algorithm is the most well-known example. So the w is given, can be as small as this quantity. But the issue is sometimes these kind of we call fast algorithms, they are not very numerically stable. So it needs a lot of tweaks to make this to work in practice. So there's still active research area. And for these kind of algorithms, if you reduce the operations, in fact, your communication pattern, the memory access pattern also changes. It's actually benefit to also reduce the communication. So there are some benefits. So there are a lot of, for different algorithms, more sophisticated algorithms that are taught in the math MA221, which is the matrix computation class, and another is parallel computing class. So the last thing I would like to spend maybe 15 minutes or so to talk about is the auto-tuning. So this example is one of the many years ago, more than, so it's 17, 18 years ago in the CS297 class project. So what they did there is they organized the 22 student teams in a class to write a matrix multiplication on this particular machine. I'm sure that was the fastest, very good machine at that time. And then they compete. So in the picture, it shows a different performance, different team. They are numbered from 1 to 22, I think. What this experiment they did is in the beginning, every team is given a blocked code to start with. So that's your baseline code, which is given. It's not the 3-nested loop. It's already a blocked version of the code, a matrix multiplication. So it's a reasonably good code. And even for that code to start with, you get about 10% of the machine peak. Okay. Then the students, they do the different optimizations. So here, this solid line just say at different teams, they get a different speed. But this solid line is the median over when your code does a matrix multiplication of dimension from 1 to 768. Okay, so this is the median. What's the fraction of the percentage peak you have achieved? And then you can see that it varies. So this number 2, this team seems to be get a very good result. And what they do is they use Intel compiler, and also they use this vector, SSE, vector intrinsics, which is provided by the vendor. So you can do the vector operations. And with this technique, also I'm sure they have some way of optimizing, clever way of optimizing the code, so they get actually very good performance. And the GSI is the graduate student instructor, the TA, it's like Max. So he did some more and get it even better. But still, compare with, even with a lot of effort here, compare with this red one, which is the supplied from the AMD, this library is called ACML, AMD library, it's vendor supplied. So you are still not, not beating them, even though you spend a lot of effort. So that's an interesting exercise. Okay, so this chart shows how hard it is to hand-tune the matrix multiplication. Matrix multiplication is relatively easy. And on the horizontal axis here, it shows the number of lines of code in matrix multiplication of different teams. And the vertical axis is the fraction of the peak you have achieved. So you can see that it's not necessarily with more lines of code you get better speed. So the best speed is this guy, which uses some intrinsics and aligned. Aligned meaning that your vector operation is aligned in memory. So each time when you access, load several data, you load the entire vector into the cache line, so that you don't waste. You don't load several entries of the cache line, so that you waste some of the entries of the cache line. So in this case, it's aligned very well. Suppose the cache line size is 8 double, then every time you load 8 double into the cache. So that's perfect. You get a perfect, minimize the number of loads you need. So that's this green one. And the number of lines of code is not too huge. It's only 256. The baseline given one is 32. It's a blocked version matrix multiplication. But then there's also automatically generated codes. You can generate, imagine you have different block size. It's a parameter. You generate different versions, 3-nested loop, 6-nested loop, 9 loops, etc. So those are the automatically generated codes. Of course, the automatically generated code, you can generate a lot of lines, different configuration, different combination. But they are not, they are performing pretty well, but not beating the best hand-tuned. So because of these kind of exercises, and people realized that to be able to generate code automatically to absorb all these different block size, to take care of all the different cache memory, speed, etc., it's important. So in industry over the past 20 years, also more than 20 years, 20, 30 years, so in various companies, they have to try to use come up with the correct abstractions to formulate the algorithms to do the good abstract way of formulating block matrix multiplication, and then write the building blocks implement very fast building blocks to be able to write high-level linear algebra algorithms to use those building blocks. The most prominent one is BLAS. We'll talk about that soon. And the issue is machines are very complicated. So it's very difficult to write a portable code. And if the vendors can write a BLAS, those basic building blocks are very fast. And that gives you a very good relief for us from a lot of hard working, the burden. So that's what this basic linear algebra subroutine is about. It's industry standard. So all the companies, the hardware providers, they implement this, they provide this almost together shipped with their machine. And the interface, you can see the interface at this public domain, netlib.org. And historically, it starts with BLAS1, like we were talking about just a vector operation. A constant multiplier vector, the DAXP operation, and dot product, those are the basic thing. So it's a vector operation. And then we know that this Q ratio is roughly 1 or 2. Something like that. It's not very good. And starting mid-1980s, then there's a BLAS2 operation. People realized that you can have to do higher level, instead of just the vector level, do the matrix level. So then it comes with the matrix vector multiplication is the key building block for the BLAS2 operation. And here, as we mentioned, this Q is still not very good. It's only roughly about 2. Okay. So it's in practice, it's slightly faster. I showed you a curve. BLAS2 is slightly faster, but not so much faster. And what's significant breakthrough is really this BLAS3. So people realize when you do, get to even higher level, try to do as much as possible matrix operation instead of matrix vector or vector operation. And then you get this benefit. So as we said, the Q, potentially you can get an order of n for many dense linear algebra operations. But in practice, for example, if you do the block algorithm, is just the order of b. And because the b size will be limited because of the fast cache memory size. So you don't get order of n, but in theory, you can get a very, very good Q ratio. So that's all the good implementation is try to get this Q as high as possible. And then we talked about LAPACK, ScalarPACK, these higher level linear algebra routines, they are built entirely on BLAS. So if there's a good BLAS3 library, then these two libraries, LAPACK, ScalarPACK including communication, so that's a separate issue. So then on each, sequentially at least, they will be very fast. Okay. And that's the picture I showed, I think, before. So you can see that BLAS2 is not much better than BLAS1. When you increase the problem size, matrix dimension is slightly better. What's really, getting you up there is BLAS3. Okay, so this picture shows a lot of machines, and this data is taken from Jack Dangara. He's one of the lead PI of the ScalarPACK, LAPACK project, together with Jim Demo here. The two groups from Berkeley here and also Tennessee have been working together for 20, 30 years for this kind of algorithms. So this picture shows many machines, and a lot of them, they are older machines, not today's machine. But the situation will be very similar if you compare BLAS2 and BLAS3. So the blue one is the DGEMM, it's the double precision matrix multiplication in BLAS, and the red one is double precision GEMV, the matrix vector multiplication. So the vertical axis is the megaflop rate. So the higher is better. So you can see that on all the machines, DGEMM is much better, get higher, megaflop rate than GEMV. It can be a lot faster, in terms of getting the peak performance. So in practice, when you tune the code, there are many aspects that needs to be taken into account. It can be very tedious. So you can have a lot of code variations. And we were talking about 3 nested loop, 6 loops, 9 loops. That's only for the block level. But then, earlier on, there was a question about the number of registers. Suppose you want to do the register blocking and taking advantage of 32 registers. There's another level of complexity. And nowadays, there are all the machine, they have a vector unit so that each operation, each hardware instruction, vector instruction, can operate 8 double precision addition or multiplication. And somehow you need to make sure this vector lane is fully populated in order to get a peak speed. So there are a lot of complications in hardware. And you imagine if you write code to take into account all these, there are a lot of different variants of the code you can write. And also the compiler behavior is difficult to predict. So even it's also a combinatorial kind of way of configure the compiler. Compiler has, say, for example, 10 flags, and each flag you have different values. If the combination of those, that will change the performance wildly. So those are the things that usually people need to worry about in terms of tuning. So then the issue is really how to automate the process. That's something called auto-tuning. So you can write some simple, you use a simple code generator. So for example, nowadays people use Python to generate a lot of C or C++ code. And then this code run the actual machine. Say 100,000 of those generated code run. Then you pick up the code, the segment of the code that runs the fastest. So that's the situation with the current auto-tuning in a simple way. And this actually started, as we saw from the class project in the CS267 homework assignment we saw in the beginning in the early 90s. And then they came up with this feedback, which did a lot of auto-tuning, use a lot of auto-tuning technique in this package so that you can run reasonably fast to get the code reasonably fast on the machine. And currently in the 267, they still use the same assignment for over the years. So every time they try to see how the students could get better and better write code. Okay. So one of the things we need to worry about is for the blocking version, for example, is how do you choose the block size? That's one of the parameters. So then very often people generate the code with different block size, then you run those on different machines. So the performance models can be useful to help you to, we talked about all the way about the performance model, calculating this M, F, and the Q factor, etc. So this could help you at least mentally to say how many code I would generate. What are the reasonable code? You don't need to generate unreasonable code. So that will reduce your search space. So one of the examples is given here is, so this is the heat map of the matrix multiplication, the performance, with a different block size. So on the horizontal axis is the number of rows in the register block, and the horizontal axis is the number of rows, number of columns in the register block. And you can see that you can get performance between 600 megaflops versus 100 or below here. So for this combination of the row column block size, the register block size, you get very low performance. The best performance is this 3. I think it's a 2 by 8 or 2 by 3 or 4. So if you do the register blocking of 2 by 3 or 4, you get a very good performance. So the difference could be like sometimes 10 times difference. So then that means you're, even for this configuration, 16 times 16 is 256 possibility of configuration. You have a bigger space to search. And how do you do the search fast when you install the library to get the best implementation? So those are the auto-tuner is part of the job of auto-tuner is to get to this point here, to nail down to this point. So I think that's, okay, so this one is the Atlas, is a free BLAS library with the auto-tuning technique in there. So this comparison is comparing on different machines on the x-axis, and the vertical is the megaflop rate of 3 BLAS libraries. One is the vendor BLAS, one is this Atlas, which is a public domain. You can get it. And then another one is F77 BLAS. The reference implementation is not optimized at all. So you can see that Atlas is actually doing very well. It's very often it beats the vendor BLAS. So with the auto-tuning, you can do much better compared to hand-coded. Okay, so that's all the materials from the lectures prepared by Jim Demo and Kathy Yellick. Do you have any questions? We still have some time. Or which part you don't you want to show a little more? I can go. Yes.
So what current package would you recommend us use?
For BLAS? Yeah. For BLAS, so Atlas is one of them. Another one, very good one, is OpenBLAS. You can Google them. Yeah. So these two are public domain. And then if you are running on the specific machine, I don't know what machine are you using usually? Intel?
Yeah.
Intel has a good library called MKL. It's mathematical kernel library. So they provide very good. But you know, this Atlas OpenBLAS, they may be as good as MKL, even on the Intel machine. Any other question? If no more questions, we can leave us earlier. I'll be here until 12:30 if you want to chat a little.